Welcome to Dr. Adrift. This video is tailored towards endurance athletes wanting to gain a better understanding of carbohydrates. The principles discussed will provide knowledge that will improve nutritional choices and optimize your performance. The people who will get most out of this video are endurance athletes who work at high aerobic intensities for prolonged periods. For example, marathon runners, swimmers, cyclists, and triathletes. If you haven't yet seen it, I recommend you watch my earlier two videos that I will put in the description below. This will help set the scene for this video. Getting carbohydrates right is crucial for athletes, as it is a predominant energy source for movement. Humans have evolved to store energy obtained from carbohydrate digestion in the form of a molecule called glycogen. Glycogen is an energy-rich molecule available to be broken down by the body when requiring energy. Glycogen storage is just like a car's petrol tank full of fuel. It is readily available to be used when called upon. When a car uses up its petrol or gasoline, the car stops. Just like when the human body runs out of its glycogen stores, the body's athletic performance is dramatically impaired. Athletes describe this phenomenon of glycogen depletion as bonking or hitting the wall. The principal role of the digestive system is to break down large nutrient molecules into smaller absorbable molecules. Carbohydrate digestion starts with the chewing of food and the secretion of amylase in saliva. Amylase is a key enzyme that initiates starch breakdown. After swallowing the food bolus, it travels down the esophagus and enters the acidic environment of the stomach. After a period of digestion, the food chyme then enters the small intestines. Here it mixes with the pancreatic amylase and allows continuation of carbohydrate digestion. The small intestines are critical for carbohydrate digestion and absorption. It is an incredible organ with a remarkably large surface area evolved for optimal nutrient absorption. If you were to lay out the lining of the small intestine, the surface area would be large enough to cover the size of a tennis court. This exceptionally large surface area is explained by the finger-like projections lining the small intestines. On each finger projection, there are further microprojections or microvilli. This structure is described as the brush border. On this brush border, the last stage of carbohydrate digestion occurs. Enzymes are present on the surface of the villi that convert carbohydrates to its smallest form, the monosaccharide. Monosaccharides are the only absorbable form of carbohydrate. Examples of monosaccharides are glucose, fructose, and galactose. These simple sugars are then transported across the lining of the small intestines and absorbed into the bloodstream. The movement of sugars facilitates water movement and therefore hydration. The nutrient-rich blood supply from the gut sends blood to the liver, where it gets processed and assimilates nutrients before being moved around the rest of the body by the systemic blood circulation. Therefore, after a meal, the blood glucose concentration rises. This stimulates release of a hormone from the pancreas called insulin. Insulin causes the movement of glucose into body tissues, including muscle. Glucose can be used by the muscle cell immediately as an energy source, or in energy-rich states stored as glycogen. Insulin also stimulates conservation of liver energy stores by promoting production of liver glycogen by stimulating enzymes responsible for this metabolic pathway. Glycogen is made up of hundreds to thousands of glucose molecules bound together side by side. In energy-rich states, more glucose molecules are added to the glycogen molecule, creating a long chain of glucose units in series. When the body's metabolic state changes and energy is required, glycogen gets broken down and glucose is released at the terminals, providing the body tissues with a readily available supply of glucose to be used as a metabolite for energy-dependent processes. An average 80 kilogram man can store 100 grams of glycogen in their liver and 400 grams of glycogen in their skeletal muscle, accounting for around 2,000 calories of energy. The amount of glycogen an athlete stores is important because with aerobic exercise, glycogen stores get broken down and used. Eventually, if working at high enough intensities for long enough periods, the stores will become empty and performance significantly deteriorates. At high aerobic intensities, the stores can become depleted within 90 minutes. Understanding that glycogen stores are important for determining how long an athlete can work at high aerobic intensities is really important. The greater the stores, the further an athlete can travel. This highlights how advantageous it is to start any endurance event with optimal glycogen stores, and to maintain these stores during the event with optimal refueling strategies. The symptoms experienced from glycogen store depletion will differ depending on whether your muscle stores or your liver stores become depleted first. For example, if you have poor race day preparation and nutritional intake is suboptimal, you may develop liver glycogen depletion before muscle. The liver is very important in maintaining the blood glucose levels in a tight range. With glycogen store depletion, there is no available glycogen molecules left to be broken down to glucose. The liver tries to compensate for lack of glycogen by producing glucose from other metabolites, but if the intensity of exercise is high, blood glucose levels can drop, leading to a condition called hypoglycemia. Because the brain is dependent on blood glucose supply for its energy needs, it is very sensitive to drops in glucose. The effects on the brain become more serious with greater drops in blood glucose levels. Symptoms may start off as hunger and dizziness, then progress to disorientation, confusion, and poor decision making. With very severe states, it can result in collapse and loss of consciousness. Suboptimal tapering periods and suboptimal carbohydrate diets in the weeks leading up to an endurance event would result in subcapacity muscle glycogen stores. This leads to a high risk of muscle glycogen depletion during the event if working at high enough aerobic intensities. The symptoms experienced are as a result of low muscle ATP levels, aka the universal currency that drives movement. The muscle cell's contractility decreases, and its ability to regulate its intracellular environment decreases also. This leads to muscle fatigue, pain, cramps, and perceived leg heaviness, ultimately leading to a dramatic deterioration in performance. Okay, so we've talked about the physiological effects and symptoms of glycogen store depletion. Let's now switch focus and focus on how to minimize the risks of getting in this situation in the first place. First, we must consider what factors influence the likelihood of developing glycogen store depletion. I've broken them down to 3 subcategories. First, the size of the tank. Second, how full the tank is. And thirdly, the intensity of exercise. Okay, so let's talk about the size of the tank. Generally speaking, the size of your liver and muscles determines the total potential capacity of storage. If you take a group of people and were able to measure total potential glycogen storage, a bell curve distribution would be seen. Assuming all other influencing factors were constant, you could state that an endurance athlete with small storage reservoirs are at higher risk of developing a glycogen depleted state compared to endurance athletes with larger storage reservoirs. For example, a person with a small liver would potentially be more vulnerable to bonking compared to an athlete with a relatively large liver. Furthermore, females on average have higher fat distribution and less lean muscle, meaning they generally store lower total amounts of glycogen and are relatively more reliant on fat metabolism compared to males. Conceptually, these are important points, but unfortunately your liver size or skeletal build is fixed and non-modifiable. However, what is modifiable is how full the tank is at any given time point. It is what you, as an athlete, need to target. An athlete's goal should be to have glycogen stores filled to capacity when on a starting line of any event. This will optimize their chances, or your chances, of adequate glycogen storage for the event and produce better outcomes. What and how much you eat, as well as your exercise regime in the period leading up to the event, will influence the density of glycogen storage. The muscle and liver cells have a set point, or in other words, an internal control system, something a bit like a thermostat in a heating system. Once glycogen stores in the cells have reached this set point, the excess metabolites start to get stored as an alternative form of energy, i.e., for example, converted to fats. Carbohydrate loading strategies create a specific environment that results in cellular signaling mechanisms, ultimately leading to cellular metabolic changes, resulting in a phenomenon called glycogen store supercompensation. I will go into this later, but essentially it is a phenomenon where you trick the body into vastly increasing the amount of glycogen that is stored. The density of glycogen stored can be increased by more than double, giving an athlete a significant advantage. The likelihood of depleting glycogen stores during exercise is also influenced by the intensity of aerobic exercise. Running speeds, terrain, running biomechanics, and physiological efficiency all determine the level of aerobic intensity an athlete is working at. Intensity of exercise can be measured in a lab and expressed as a percentage of VO2 max, or it can be roughly extrapolated by monitoring heart rate during exercise. The reason this is important is firstly, at higher intensities of work, more energy stores are used. And secondly, the predominant stores used at this level of intensity is glycogen. At lower aerobic intensities, fat stores are the predominant energy store used. This information allows athletes to assess risk of bonking or hitting the wall. If you are exercising at low aerobic intensities, then it is less likely you will become depleted. But if exercising at higher aerobic intensities, the risk is vastly increased. The duration of high-intensity aerobic work is also critical. The longer you work at this high intensity, the more likely you are to deplete your glycogen stores. Glycogen stores can become depleted at this intensity within 90 minutes. This highlights that activities like marathons, which exceed this time period, are generally higher risk for glycogen store depletion. There is clear evidence that carbohydrates before training and during training enhance physical performance and have positive cognitive effects. Carbohydrates post-training have also been demonstrated to improve recovery. However, the nutritional strategy or philosophy employed by an individual will vary depending on their goals, ability, intensity of training, and whether they are in a training block or getting ready to compete in a race. For example, a recreational athlete has different needs to an elite competitor, and nutritional strategies should reflect this. There is not one fixed strategy suitable for every situation. There are nuances and controversy in this field. However, one thing is clear: carbohydrates are king when it comes to race day nutrition. Don't forget this. Let's now focus on carbohydrate quantity. Whether you are a recreational or elite athlete, it is useful to think about your nutrition in two separate categories. That is, training carb strategies and competition carbohydrate strategies. There is strong evidence that high carbohydrate diets enhance performance and should be the mainstay of recreational athletes' diets to avoid the risks of bonking and to improve athletic performances. The more active an individual is, the greater amount of calories needed to be consumed. Chronic low-calorie intake impairs the body's repair and increases risks of injuries. The relative proportion of carbohydrates ingested compared to proteins and fats should also increase with greater levels of activity. In general, for individuals undergoing endurance training, they should be consuming the following quantities of carbohydrates. For moderate exercise levels, 5 to 7 grams per kilogram body mass per day. Heavy exercise, 6 to 10 grams per kilogram body mass per day. And in extreme loads, even more carbohydrates are required. Plants store their glucose obtained from photosynthesis in the form of starch. This acts for plants somewhat like the mammalian store glycogen. Starch is stored and readily available to be broken down to supply energy when required to do so. Starchy foods are a great source of high carbohydrates, and for the majority of training periods should be a mainstay of a recreational athlete's diet, as the plentiful supply promotes glycogen storage and ensures adequate stores for exercise. However, over the last 10 years, there has been a shift in endurance nutrition philosophy that some elite athletes are incorporating into their nutritional regimes. This new philosophy has been termed train low, compete high, formerly referred to as periodized carbohydrate strategy. The concept is that during training blocks, the body's metabolic system can be trained in response to certain stimuli, just like any other system in the body. It involves a conscious and well thought out intentional period of training at depleted muscle and liver glycogen states. The idea is that exposing the body to such states for prolonged periods stimulates intracellular signaling in the muscle and liver cells, leading to a reactive upregulation of certain gene expression involved in metabolism. The adaptive changes lead to the muscle cells having enhanced ability to use fats as an alternative energy source, which preserves glycogen stores. The cells also adapt to becoming increasingly more sensitive to glucose uptake and has greater potential to store more glycogen. And finally, the mitochondria, which is vital for aerobic metabolism, increases in numbers. When the adapted cells get subsequently exposed to a high carbohydrate supply, which intentionally occurs from the ingestion of high carb foods in the lead up to a race, it translates into greater stores of glycogen and more efficient use of it, leading to enhanced athletic performances. This train low, race high approach has risks and limitations. Training in low glycogen states will limit the ability to train at high aerobic intensities, as the athlete has lower threshold for muscle fatigue, which reduces the training workload sustained and will reduce the stimulus for other adaptive changes to take place in other fitness parameters. Low-carb diets have implications on athletes' mood, increasing the likelihood of depression and emotional instability. Low glycogen states will also reduce the immune function and increase the risk of picking up infections. Furthermore, calories should be adequately met from eating alternative macronutrients, for example proteins and fats, to avoid prolonged catabolic states. If chronic suboptimal calories are taken in, it can lead to increased risk of muscle injuries. It is for these reasons that it is argued that the train low, race high approach, if instigated, should be for temporary phases of a training block, well planned out and arguably only needed for elite athletes. The high carb diet approach is adequate and safe for most recreational athletes to achieve their fitness goals. Furthermore, the jury is still out whether the high carb philosophy or the train low, race high approach is holistically superior. For those interested in learning more about the train low approach, here are 3 strategic regimes you could incorporate within your training. The important thing to remember with the train low approach is that the adaptive changes come about from exercising in a low glycogen store state and does not necessarily correlate with the carbohydrate quantity ingested. The strategies are about creating periods of low muscle glycogen to stimulate adaptation of those cells. The 2 sessions a day training, as the name suggests, involves a morning training session followed by an evening training session. The morning session is high intensity aerobic exercise that depletes glycogen stores. After the session, there is an intentional restriction of carbohydrate intake, which continues into the afternoon. This further depletes the glycogen stores, and the second training session is commenced in the afternoon. The day then is finished off with a high carb dinner to replenish stores and promote recovery. An example of fasted training is eating dinner as normal, followed by bed. During sleep, we are in a fasting state, and our liver glycogen stores get used to maintain our blood sugar levels in a tight range. On waking, a training session is performed. In this state, the liver glycogen stores are depleted, but the muscle stores are okay. This trains the body in utilizing fats as an alternative energy source and will stimulate cellular adaptations. Sleep low, train low. This involves an evening training session followed by a restricted carbohydrate meal in the evening. The meal needs to contain protein and fats, but low carbohydrates. Sleep as usual. Then the following morning, perform a fasted training session. This session needs to be done at relatively low to moderate aerobic intensities to further facilitate fat oxidation, or in other words, using fat as an energy source. If you perform this fasted training session at too higher aerobic intensity, it will pose significant risk to you developing hypoglycemia or bonking, as at high aerobic intensities, glycogen is the predominant energy source, which in this fasted state is currently depleted. Here is an example of a carbohydrate restricted meal that provides substituted calories in the form of proteins and fats. In order for insightful food and carbohydrate selection, you need to consider not just how much carbohydrates are in the food you are eating, but also the glycemic index of those carbohydrates. The glycemic index serves as a numerical indicator representing how quickly after consuming carbohydrate-containing food it affects blood glucose levels. Digestion and absorption are the time-limiting factors that determine how quickly the carbohydrate-containing food affects blood glucose levels. The time taken will vary for different carbohydrate-containing foods. Foods with a high glycemic index are rapidly digested and absorbed, causing a spike in blood glucose levels, whereas foods with low glycemic indices take longer for digestion and absorption, creating a blunted and gradual blood glucose rise. From a health perspective, glycemic index is a very important consideration for diabetics. However, I'm not focusing on this perspective. I'm merely coming from an endurance fitness perspective and discussing how an understanding of glycemic index can influence food selection for short-term performance reasons. An awareness of glycemic indexes becomes particularly advantageous when desiring rapid availability of glucose. Nutrition during exercise and in post-exercise recovery phase are scenarios when selecting high glycemic index carbohydrates are advantageous. Furthermore, an athlete may select foods with a high carbohydrate quantity but low glycemic index profile for training days to give a sustained, prolonged glucose absorption over relatively long periods of time. There are data sets online of glycemic index values of foods, but having an understanding of what general factors can influence glycemic index will assist you in estimating where likely the food in question lies on the glycemic index scale. One might assume that large molecules, such as polysaccharides like starch, will naturally have lower glycemic index compared to smaller molecules like simple sugars or monosaccharides. This might be based on the inference that they will take longer to digest and subsequently be absorbed because of the larger molecule size. However, this assumption is not always correct. Let's take fructose for example. Fructose is a simple sugar or monosaccharide that has an extremely low glycemic index. The reasons for this are twofold. Firstly, it gets absorbed by the intestines very slowly, and secondly, after absorption, it takes time to be converted by the liver to glucose before it can have effect on systemic blood glucose levels, meaning that this simple sugar has a lower glycemic index than an even complex polysaccharide such as starch, which consists of hundreds to thousands of glucose molecules. Three-dimensional shapes of carbohydrates are also important, as demonstrated by the molecule starch. Starch molecules are arranged in two types of three-dimensional shapes, one called amylose and the second amylopectin. Amylose consists of a chain of glucose units twisted into a densely packed helical coil, whereas amylopectin consists of a highly branched structure. Starchy foods with high amounts of amylopectin are digested more rapidly due to the highly branched molecule, allowing greater surface area exposed for digestive enzymes to break down the molecule. This is useful as the specific ratio of amylose to amylopectin in starch-based foods will give an idea of the glycemic index of that food. High fibre foods are generally associated with lower glycemic index values, as fibre delays gastric emptying and slows glucose absorption, something you might want to avoid around the time of competing. Consuming foods with high saturated fat content will decrease the glycemic index of carbohydrates co-ingested, as fats require a longer period of digestion and delays the transit of food through the intestines, subsequently slowing absorption of monosaccharides. Whether a food is raw, ripe, or cooked will also influence its carbohydrate glycemic index. Raw foods will take longer for digestion compared to their ripe or cooked equivalents. The same principles applies when comparing unrefined to refined foods. There will also be individual differences between people's digestive systems in how they digest and absorb carbohydrates. This will influence personal preferences with food selection. The extremes of which are seen in disease states like lactose intolerance, where the person can't digest and absorb dairy products due to the deficiency of the enzyme lactase on the brush border of the small intestines. Here is a diagrammatic representation of glycemic index for common carbohydrate-containing foods. Generally speaking, legumes, pasta, fruits, and dairy products have low glycemic index at 55 or below, whereas breads, breakfast cereals, rice generally have high glycemic index. When it comes to food selection and the effects of that food on the body, both the food's carbohydrate quantity and glycemic index need to be considered in tandem. Glycemic load is a term used to quantify the overall glycemic effect of a food portion. A high glycemic load of a food represents a greater expected blood glucose rise and associated insulin release compared to a food with a lower glycemic load. It factors in both carbohydrate quantity and the glycemic index of that food. Don't be too distracted with the formula. I'm using it just as a useful tool to express the interplay between glycemic index and quantity. The importance of both these factors can be seen when looking at watermelon as an example. Watermelon has a very high glycemic index, but the overall total amount of carbohydrates in a 100-gram portion is small. Therefore, the glycemic load is very low, meaning the glycemic load may not be sufficient for the carbohydrate requirements of the athlete. 100 grams of white cooked rice has a glycemic load of 18.5. Therefore, to get the equivalent glycemic load from eating watermelon, you would have to eat over 3 times as much watermelon compared to white rice, equivalent to around 320 grams of watermelon. In other words, white rice has the same glycemic load at around 1/3 of the portion size to watermelon. Don't get too focused on the numbers. An understanding of the principles discussed is most important. For an endurance athlete, there are specific times when consuming a high glycemic load is advantageous, and when eating a high glycemic load is disadvantageous. The timing of carbohydrate feeds is the final factor that needs to be explored. This will be addressed in the second part of this video series. Part 2 will focus on competition carbohydrate choices. Core themes include carbohydrate loading strategies, race day carbohydrate nutrition, and finally recovery strategies for rapid glycogen replenishment.